Here is a geometric puzzle. A country has n towns. Okay, so let n be at least 2. A country has n towns, the distances between which are distinct. That's just so that I don't have to mess around with ties. You start in a town, okay, this is part A of the exercise. You start in a town A1. From there, you travel to the town A2 that is furthest away from A1. From there, you travel to the town A3 that is farthest away from A2. So basically, you try to travel around the country, each time taking the farthest possible town. So to illustrate it, here is an example of a country with just 4 towns and the distances between them, well, approximately, but still. They're precise enough so you can tell which of them are longer. So, for example, if the country has 4 towns, A, B, C, D, as shown on the following picture, and you start at A, then where do you go? The possibilities are B, C, and D, but B is pretty close. D is further away, but still not as far as you want. C is the farthest away town, so you go to C. Where do you go from C? Well, the options are B, A, and D, and D is the farthest away, so you go to D. Now, where do you go from D? A, B, and C are the options, but C is the furthest away, so you go back to C. And then, of course, you have to keep walking between D and C, because once you have, I mean, the second time you're at C, you won't have a different choice than the first time. So once you went from C to D, and if you're again at C, you will, of course, again go to D. There is also a part B of the exercise. Oh, what is the claim of the exercise? Prove that if A3 is not the same as A1, so if you did not get back to the original town after just 2 moves, then you will never return to A1. And part B is the same problem, except with closest to instead of farthest away from. And of course, when you say closest town, you don't mean the town itself. You don't go from A straight to A, as that would not be a very interesting journey. So, example, in the above country, if you start at C, for example, then you go to, well, which of them is closest? A, D, and B. B is closest. So C to B. From B, you go to A because A is the closest to B. From A, you go back to B, and then you keep oscillating between A and B. So, how do you prove this? And this time the monovariant is particularly simple. I won't even speak of a monovariant. So the idea is each leg of the journey is at least as long as the preceding leg. In other words, we have the distance A1, A2 is less or equal to the distance A2, A3 is less or equal to the distance A3, A4, and so on. Why? Well, let's prove this inequality. The others are exactly the same argument. So when you go from A2 to A3, you're picking the furthest away town. Now, if this distance was bigger, then the furthest away town would not be A3 because A1 would be even further away. So you would have to go to A1 instead of A3. But since you're going to A3, it means that A3 is furthest away from A2, and therefore you get this inequality. Furthermore, if A3 is not equal to A1, then the first of these inequalities is strict. Why? Because if it was an equality, then keep in mind that the distances are distinct. This is where you need this. So if A1, A2 would be A2, A3, then the segment A1, A2 would be equal to the segment A2, A3. Not just the distances would be equal, but the actual line segments would be the same. And then A1 would be A3, but we assume that this is not the case. So you can basically improve this chain of inequalities using this. And now assume, of course, that A3 is not A1. Okay. Now assume for contradiction that you do return to A1. That is, AM equals A1 for some M at least 2. And 2 is actually impossible because you always go to a different town. So you never just stay in a town. So M at least 3. Therefore, we can take this chain of inequalities and break it up at AM. And this is, of course, AM minus 1, A1, because AM is A1. And you can even rewrite it like this, A1, AM minus 1. Distances are symmetric. Now, however, A2 was chosen to be the town furthest away from A1. Hence, in particular, the distance A1, A2 is larger or equal to any other distance involving A1, in particular to this one. And so between these two distances, we have two conflicting inequalities. This one is smaller, but this one is also greater or equal. So this is a contradiction. And so we're done. And part B has exactly the same argument. We just need to turn all the inequality signs around, which of course really reveals that this is not a geometric problem. This is a problem about some kind of notion of distances which have to be symmetric so AB is ABA, but other than that, it doesn't really matter what they are. And further away is kind of the same as closer.